in-order fetch. So we have an in-order front end, and we have out-of-order issue, write back, and commit. So what this is going to try to do is we're going to try to fix some of the problems that we saw here, where we'll actually had, let's say, this instruction here, this add, is waiting to issue because our issue was in order. So that instruction could issue. All of its inputs are ready. R11 was written right there or something like that. So R11 is ready. It's ready to issue. But because we have in-order issue, by definition, we can't issue out of order. So now let's look at a machine where we can issue out of order. So we can actually move it to the execute units, do our register fetch out of order. So to do that, we actually have to add another data structure. And this data structure, we're going to call the issue queue. And this is going to be something like an associative FIFO, but it's not going to be FIFO. We're basically going to store instructions into it, and then we're going to put instructions into it in order because our fetch is in order, or our front end is in order. But we're going to pull out of it out of order. But we have to be a little careful because when we go to pull out of that data structure, we have to make sure that all of the appropriate registers are ready. So all of our dependencies are ready, or at least somewhere in the bypass, or we can go pick it off the bypass by the time it actually needs the value, or in our bypass stage. Let's take a look here. We still have an architectural register file. We got rid of all of that complex reorder buffer stuff on this example. So we don't have a reorder buffer. We don't have a store buffer. We have out-of-order commit. So we're going to have the same problems we had before with precise exceptions in this pipe. But this is going to give us sort of an easy introduction to understanding what the issue queue looks like. So the issue queue gets written when instructions enter it. So sort of at the decode stage, this is itself is a register structure. So it's like flip-flops in here and a bunch of logic and stuff. So you can't just go from this stage to this stage in the pipe without having any registers. So it gets written there, and things are basically going to update into this. So when things actually end up in the architectural register file, we're going to mark bits in the issue queue saying, oh, that register you're waiting on, it's now ready. And if you get, let's say, 2 registers that are ready and you're dependent on 2 registers, you can issue. And we can issue out of order. OK, so I have read and write here in the issue stage. Why do I have that? Well, when you actually go to issue it, you basically want to mark that instruction as, oh, yeah, I actually did issue this instruction. You want to, sometimes people build this as actually remove the instruction from the issue queue. In this basic case, we're going to leave it in the issue queue until the end of the pipe because we need some way to track the liveness of the instruction. But the next processor, we're basically going to think of it as sort of a, I won't say FIFO because it's not strictly first in, first out. But it's a data structure where you can put stuff in and then move stuff out of. So it's a buffer or a multi-entry buffer. OK, let's take a look inside the issue queue. And this is assuming something like MIPS. So in our issue queue here, we're going to have, first of all, we're actually going to have the opcode because we're going to have multiple instructions sort of ganging up in here. So it's possible there can be like, I don't know, in this case, 1, 2, 3, 4, 5. There's 5 instructions just sort of sitting in this data structure. So you sort of slacken, there's a buffer and slack in the front of your pipe, effectively. You might need the immediates values, because that's sort of part of the opcode, or part of the instruction. And then we're going to basically have things for the 3 different registers. And what we're going to put in here is we're going to put the register identifiers. So here, let's look at the sources first, because that makes a little more sense. The V bit is going to say that this instruction needs the source. So it's possible that, as we said, there's some like immediate instructions don't read both source operands. So for an immediate, only one, probably this valid bit is going to be set, and this one's going to be 0. The p bit is pending. So what that means is somewhere later in the pipe, there is a in-flight instruction that writes to that register. So we're going to basically track that with a bit here, saying that is still pending. Now, the reason we actually have to keep that pending information and the validity information sort of separate, and why we need to keep both of them, is it's possible that multiple instructions could light up simultaneously as being ready to go. So if you have, let's say, 2 instructions that are both dependent only on register 5, and register 5 is not ready, it's the destination of a multiply. But then register 5 gets written, it's going to actually clear the pending bits, so it's no longer pending. And it might be in multiple places. So it might be like here and here, maybe even there. It's going to clear the pending bits in whoever's trying to read register 5. And then because we're only, let's say, going to have single issue on this processor, you can only pull one thing out at a time. So you need to sort of pull one thing out, and you need some way to leave the other instruction in the issue queue, having all of its operands ready. So that's how you do that. OK, so how do we figure out if an instruction is ready? Well, we see if it actually uses it, that the operand uses the particular operand identifier, and we see if it's pending. And then we have to check the other for 2 inputs. We need to check the 2 inputs. And then we also have to make sure there's no structural hazard somewhere else in the pipe, like if we're trying to schedule write ports. And we're going to use the scoreboard to do that. The other thing is if we want high performance, we probably don't want to have to wait for values to get to the end of the pipe. So in reality, this is going to get more complicated because it's going to be these things plus information coming from the scoreboard, which says when a particular register identifier is ready, or when a particular register is ready. Let's talk about the destination here. This just tracks whether an instruction writes a destination or not. And like I said, in these basic pipelines, we're going to leave instructions in the instruction queue until they get to the end of the pipe. And when it gets to the end of the pipe, this is where we go to check to see what other locations we need to sort of clear out. So if there's an instruction, let's say, sitting here, which has the valid bit set, and it's writing to register 5 as the destination, when that instruction commits, we're going to clear it out of the issue queue, and we're going to say, oh, well, it wrote register 5. Let's scan through all these other places and look for places that say register 5. And if they say register 5, we are going to flip the pending bit from pending to not pending anymore. And we're going to remove the instruction from the issue queue. OK, so centralized versus distributed issue queues. In a sort of logical sense, in a perfect world, it's probably nice to have a big centralized issue queue. You can scan over all the instructions. You don't have to sort of look around. But this can sometimes be harder to implement because you have to put all of your instructions in one location. And sometimes they don't necessarily sort of cross-communicate very well. Like floating point units, they have floating point registers versus integer register files or something like that. They don't necessarily need a whole lot of communication. So you could have distributed instruction queues where you sort of steer, let's say, here the execute or ALU and memory ops to one of these for these functional units, and you have a different instruction queue just for multiplies or something like that. I'm going to put a paper on the website for you guys all to read. It's Tomasulo's algorithm. It's a very famous paper. And in that, they talk about distributed instruction queues. Strangely enough, sort of the first place in literature that these instruction queues showed up was around that time or in that paper. And they actually go straight to the distributed version and kind of skip the centralized version, which I always found a little bit odd. But lots of people build centralized ones today. one of the reasons that I think the Tomasulo algorithm people went for this distributed one first is because they were actually implementing on multiple discrete chips. So they had an issue queue per chip. So they had like a floating point chip and an integer chip, and they steered the instructions, and they didn't want to have one data structure that crossed two chips. Today we have lots of integration, so we don't have to worry about that as much. Okay, so I just wanted to briefly say this was the question that came up last time, and scoreboards. If you have to worry about write after write hazards in the pipe, the things we are talking about today, we didn't have to really worry about that, but the stuff we talk about next time, we're going to have to think about better scoreboards. It looks the same as the previous scoreboard, but you might need to keep the functional unit, or you need to keep the functional unit number, or some bits that represent the functional unit, and then those march down the pipe versus ones marching down the pipe. You have, let's say, different numbers like 1, 2, 3, or you have other things marching down the pipe. But that's only if you have to track write after write hazards. Okay, so that was just a quick aside. Let's look at this in order fetch, out of order issue, out of order write back, and out of order commit processor in a pipeline diagram. And I'm going to show a new little thing in our pipeline diagram here. We have a lowercase I, which means the instruction enters the issue queue. And then when it exits the issue queue, it just starts going down into the issue stage of the pipe. And I'm trying to think, what do I want to show? This is not that complicated of a drawing. Here I'm actually showing the issue queue, what is in the issue queue. So I have 3 issue queue slots, because this is a relatively simplistic pipe. This first instruction, which goes to execute, register 2 and register 3 are just already ready, so we don't have to worry about it. But an example of something that's more interesting, let's say, is I don't know, where's a good one? Here we go. This will enter the issue queue, but register 12 does not become ready until late. So once that comes ready, we can basically start pulling things out of the issue queue and issue that instruction. So that shows up. Let's see if we can show that here. Register, what is this, 14, 12. OK, so this one here, we're waiting for that to happen. Let's see. Yeah, we're waiting for, no, where is it? 12. This add. This pipeline diagram looks wrong. Yes, that actually is what I wanted to show here. This is interesting. The value actually becomes ready early. But, is that what's actually happening here? The value becomes ready at the end of this execute stage, but it can't go to issue at that cycle because there's something else issuing, so it has to be pushed out. So we're only doing a single issue per cycle. If we had multiple issues, you could think of something more interesting happening here. Yeah, so this is a really complicated case, because if we pull this back, let's say to here, we get a write back hazard. The W would conflict with the other W. If we try to issue here, sorry, that was if we issued here. If we try to issue here, we get a structural hazard on the issue, so it actually gets pushed way out there. So it's kind of a bummer. So sometimes you just lose. OK, so here's an interesting case. So let's assume that all the instructions are preloaded into the issue queue. So showing this, we have fetch, decode, issue, 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 and basically these things are just sort of sitting in the issue queue. And then we start looking. What happens? Does the performance get better than the previous example? So interestingly enough, even if you sort of issue everything into the pipe early and then just sort of fill up your issue queue, pulling out of the issue queue can still be a limiter, and the number of ALUs can still be a limiter. So there's other structural hazards. The performance of this code and this pipeline does not actually get any better, which is sort of interesting. You'd think, oh, well, I don't have to wait for things to sort of drivel into my instruction queue. I just sort of preload my instruction queue. But the performance really doesn't end up being better. So this motivates us going to both out of order mixed with duplication of structures. Like maybe we can issue 2 instructions at the same time, and maybe we can have 2 ALUs. So this is motivates us having a superscalar.